Okay, so we've come pretty far in our discussion of electricity. Now that we have some sense of what voltage is, at least in the conceptual sense, let's step forward and talk about voltage in the practical sense. So we all have some experience with voltage, right? Whether it's the AA batteries that we put into our Walkmans, or it's the 9-volt battery that we accidentally put into another appliance and ruined it. We all understand that voltage has something to do with the ability to provide power. So let's talk about what a circuit is. Alright, so the simplest DC circuit that we can come up with has 3 parts. It has a battery, which is going to provide energy to the charge carriers. It has a resistor, which is going to take energy from the charge carriers, and it has wires, which connect the battery to the resistor. So before we get started on our analysis of the circuit, I should note that I'm going to do the analysis assuming that the charge carriers are positively charged. Now, in modern physics, we understand that it's electrons that are actually moving through wire and giving us electricity. Because science didn't discover electrons until after it already had started studying electricity, the convention is to do these diagrams and talk about electricity in terms of positive charge carriers. So we're going to work within the convention, and then you can just turn everything around when you're working with electrons. So a battery has 2 terminals, a positive terminal and a negative terminal. At the positive terminal are concentrated positive charge carriers, and at the negative terminal are concentrated negative charge carriers. Now, recall from our discussion of electrical fields that oppositely charged particles attract each other. So what we can see is that there's a natural attraction between the positive charge carriers in the positive terminal and negative charge carriers in the negative terminal. Separating these 2 terminals is a boundary across which the positive charge carriers and negative charge carriers cannot pass. This is good. We want to force the positive charge carriers to move to the negative terminal through wires. We're going to use those charge carriers to do work. Oftentimes when we think about some sort of object or particle doing work, we think about it losing kinetic energy. So when I throw a ball full tilt at a wall, that ball will do work on the wall as a consequence of it losing its kinetic energy, and that kinetic energy being converted to work done on the wall. However, charge carriers through a circuit have a constant velocity, what we call a drift velocity. So it's not a loss of velocity that's converted to work. Instead, it's a loss of potential energy that's converted to work. As a charge carrier moves through a circuit, it will eventually encounter a resistor. The resistor will essentially drain the charged particle of its potential energy while not changing its kinetic energy. It's this loss of potential energy that will be used to do work. Now, this might sound like somewhat of a weird concept, but imagine you have a baseball in your hand and you're standing on an ice rink. Now, you throw that ball from your hand, which is 6 feet above the ground, and as you release it, the ball begins to fall. The potential energy that ball had due to its elevation above the ground is being converted to kinetic energy. However, the ball's forward velocity never changes, even when it hits the ice, because we're going to assume that the ice provides a frictionless surface. So the ball, which was initially traveling at 60 miles an hour, will continue to travel at 60 miles an hour, but the ball has lost potential energy. That potential energy will be converted to work when that ball hits the ice. A charge carrier moving through a circuit is no different. Its kinetic energy is not going to change at all. It's always moving in the same direction with the same speed. However, it's losing potential energy, and at that loss in potential energy that we harvest to burn a light or to play a CD. If the battery initially instilled in each coulomb of charge 1.5 joules of energy, that energy will be lost at the resistor in the form of heat, light, sound, what have you. So once the charge carrier gets back to the negative terminal after it's made its way around, it has no more potential energy left. It can do no more work. But what the battery does is it acts as a lifting device, gives the charge carriers potential energy so that they can go through the circuit and again impart their potential energy on the resistor. It isn't a bad idea to think of a battery as a lifting device. The battery is giving the charge carrier potential energy in the same way that I can give this book potential energy by lifting it up above the ground. Okay, so this is good. So now we understand that the battery is a lifting device that instills in charges some amount of energy once they have moved through the circuit. We know that the energy imparted to the charges moving through the circuit is drained off by the resistor. The potential energy harvested by the resistor is used to do work in the form of light, sound, running an appliance, etc., etc. So we've talked about voltage, but we really haven't talked anything about current. We hear about current all the time, so what is current? Current is the amount of coulombs that move past a particular point in 1 second. The unit for current is the ampere, and the ampere has subunits of coulombs per second. So current is really just a measure of how much charge is moving past a certain point in a given amount of time. Now we also need to say something about the resistor. The resistor is important because it provides resistance in the circuit. If we go back to our example of a baseball being thrown above an ice rink, we can think about the ice rink as providing resistance to the ball's downward movement. If that ice rink wasn't there, the ball would keep moving down. But because the ice rink is there, it's in a position to be worked upon by the ball. It provides resistance to the ball's path downward. Similarly, a resistor is going to be in a position to resist the flow of charged particles through a circuit. We have to have resistance in the circuit in order to harvest the potential energy that's imparted upon the charge carriers by the battery. Resistance is measured in units of ohms. An ohm has subunits of volts per ampere. So let's put all this together so we can do some deeper analysis of circuits. So I want to introduce an equation. V, which is voltage, equals I, which is the symbol for current in amperes, times resistance, which will be in ohms, which has subunits of volts per ampere. We can use this equation to help us find the current flowing through a circuit. So if we know the voltage that is imparted upon the charges by the battery, and we know the resistance due to the resistor in ohms, we can find the current traveling through the circuit. If you work with this equation a little bit, you'll be able to see that voltage usually stays constant in the form of a battery of a constant voltage or what have you. So as the resistance in the circuit increases, the current decreases. Another way of saying this is that current and resistance are inversely proportional to each other. Now we have a bunch of unique language to discuss electrical circuits. We're talking about resistance and current, but actually what we're really talking about is flow. It's very easy to think about current in the same way that you would think about flow of water through a pipe, right? So if I were to stop a pipe with some sort of blockage, right, the water moving through that pipe would move more slowly. It's the same thing when we're talking about resistance in a circuit. The more resistance you have in the circuit, the slower the flow through that circuit. That's all we're saying. Now, let's talk about how we get power from a circuit. So I want to introduce another equation, which is P, which is power, which is going to be in watts, is equal to I, which is the current, times V, which is the voltage that's imparted on the circuit due to the battery. We can use this equation to help us figure out what kind of wattage we're going to get from the circuit that we've set up, the particular battery that has a particular voltage, and also with the kind of resistor we have. You'll see that the higher the current and the higher the voltage, the greater the power output by the circuit. We can also manipulate this equation with our former V equals IR equation to get us versions of the power equation that we can use if we, say, don't have one value or another. There are a lot of different ways to write this. It's just useful to be able to manipulate this equation so that you can find power fast. So you might be wondering what all of this has to do with MCAT and the study of medicine. Well, there's one instance in which charge and flow and voltage are readily apparent, and that is in axons and nerve impulses. So we know that there are electrical gradients set up by the nerve so that you have a voltage across the plasma membrane. The inside of the nerve cell is negatively charged due to the density of negatively charged proteins within the cell and a relative lack of positive charge carriers, whereas outside the cell you have a relative abundance of positive charge carriers. We use that electrical gradient to create movement of ions across the plasma membrane, and that movement of ions across the plasma membrane is what initiates action potentials in nerve cells. Without the presence of this voltage, our nervous system would cease to